Hello everyone, welcome to today's DWF repair bench. And after quite some time, after the last time I've dealt with this board, I'm back with the arcade Galaga bootleg, called Gallag. This is a 2-board arcade game set, and I decided to use a little 9 inches broadcast monitor, and most of the times the games boot, but it seems responsive to player start and also credits, or sometimes the credits never stop incrementing. Well, so it's a bit unstable, so let's see what we can do to troubleshoot this arcade game. Let's see how it runs. So I will play a bit and see if looks good on the emulation, and then carry on with the repair. Yeah. Okay, the first real big issue is this schematic is not correct for this board, and the clue is this chip, for example, but also this one is indicated in position 12E, 12L, but on this PCB last row is 11. So another thing is this CPU Z80 is position 10E, but all CPUs are on row 5 or 6, nothing on row 10, no CPUs. So basically I have to reverse engineer as much as possible of the schematic to understand what's wrong. And another thing that's not correct is this pin out of the main connector. Fortunately the power supply are correct, but I had verified the big tracks on the power supply anyway before making the adapter. But according to this pin out, we should have on parts side A, B and ground, and okay, CD +5, and that's okay, but E and F are basically unconnected. A, B, C, D, E, F are connected. So the first connected is actually A, F, it's the G. Oh, well, there is no G here, but anyway, these first two after the 5 volts are floating, unconnected anywhere, so it's the H, E, F, H with no G. Well, no problem, the important is that I know. So I have also to determine the correct pin out. Okay, one of the possible behavior the machine at the moment, as you can see from the sound, if you know the game, it's constantly sensing a coin. This is the sound when you insert a coin. the machine is playing and your ship goes on the right part of the monitor and it starts firing alone, but of course the signals on the inputs are not allowing this, so it doesn't always do the you see the sound sometimes it stops. I don't know if it's the CPU executing something else or the actual circuit, so I'll try to investigate this problem first. Like most arcade games, board these has a built-in service mode, and it says RAM OK, ROM OK, and no shorted inputs because otherwise it will make some sounds if I touch inputs. I can trigger different sounds, I can move between sounds with joystick controls that are the first two contacts. So there is really no shorted input, or inputs are responding fine as far as I can tell. Just triggering sounds. Well, I don't know. Difficult one, this one. So I will have a look around again on the various schematics and see if I found something. This mode after repairing the truck, and it seems that was the real problem, why the sound is not working anymore. We are always without the sound ROM, but if we probe sounds now, we have of course random sounds, and I can cycle between different sounds like before, but of course all sounds look not very meaningful, but they change. So okay, the problem of the sound has been solved, probably after I get a replacement ROM. Who knows why that truck burned up. Maybe me probing around and didn't realize I made some short circuit with the probe or something, but didn't realize really because when I powered it up it started not working. Well, anyway, one less problem, and we can go back hunting for the original problem. So I decided to change the approach for this repair and have a quite a long pause from probing around mostly blindly on the with the oscilloscope and other test equipment on the board, and I decided, of course, that this schematics was not good enough. Because there are basically two different schematics for the Galaga bootlegs floating on the network. One is called the Gallag green, and another is called the Gallag blue. The difference should be the color of the solder mask. And what is not good with both the schematics is they are both incomplete. The Gallag green is missing half of the video board, and the Gallag blue is missing half of the PCB, the CPU PCB schematic, and both of them have terrible quality. So I decided to almost completely reverse engineer the CPU board for the moment, with the help of multimeter and checking connection, reporting back the schematic on KiCad and so on. So I thought be explaining what I learned about this copy of the original Galaga PCB CPU. And as you may know, the original CPU board has a lot of custom chips that render the schematic of the game much simpler. Anyway, I tried to reverse engineer as much as I could with the help of course of the original Galaga schematic, the help of the bootleg schematics that can be found that sometimes give me some shortcuts to find the correct connections. And I divided so far the schematic in different sheets, as you can see, like the root where all the common parts have been reported, the 4 CPUs, and the daughter board, the little daughter board that is part of the first CPU circuit. So I thought we'll start with what is the main CPU. It's main CPU because this one starts at the power on reset, works alone until it's made some self-test of the board, and then can start all the other CPU because of it can raise their reset signal. But anyway, this one has 4 EEPROM in its private address space. They are 2732, so it's 16 kilobytes of code. All the other CPU has only 1 EEPROM in the private space, so each of the other CPUs has 4 kilobytes of code maximum. And there is a shared address in data bus that is accessible directly from the 3 main CPUs, the 3 Z80, which were the original game board also. And each of these 3 CPUs has some 3-state drivers that can be enabled from this signal when the CPU wants to use the shared bus. I called the A bus, the private address bus of each CPU, and AB the shared address bus, and DB the shared data bus, and the D signals are the private data bus of each CPU. So the daughter port is actually the shared data bus interface for the main CPU. It happens with 2 chips actually. 74LS373 is used when the CPU wants to read the shared bus, so during a read access, data can flow from the DB side to the private data bus. In a 74LS244, when the CPU wants to write a byte on the shared bus, so the data flows from the D1, the D1 to D7, D0 to D7, sorry, which is the private bus of the CPU, to the shared bus. Of course, the data lines are shuffled for routing purposes. We found it was easier probably to route signals with all these chips. So the fourth CPU instead is actually not accessing directly the shared bus. This one was in the original Galaga from Namco, a microcontroller, Fujitsu microcontroller with internal RAM, ROM and I/O ports. And this bootleg, this copy, they substituted the microcontroller with another Z80 CPU, another EEPROM, 1 kilobyte of static RAM divided in two 2114 chips, and quite some latches and buffers to read the controls, produce a part of the sound. I think this is the explosion sound, but I went much far with didn't go much far with reverse engineering the sound because it's working. So this CPU can directly read the state of every game control, player 1 right, player 1 left. These are some of the controls that I correctly identified. Player 1 start, player 2 start, because these controls can be understood from the service mode. And then the method that the CPU communicates with all the others is it has two latches. One is write only from the CPU and the other is read only from the local CPU. So the signal with the black label are local signal, and this light color is KiCad hierarchical label. So it means the signal comes from another schematic sheet. And so the CPU can write a byte at its 7,000 hexadecimal memory location, and the other CPUs can read the same byte to the shared data bus by using this other signal, and the local CPU can read this latch that can be programmed with another byte from the shared bus and using this write signal. If I remember correctly, the signals are produced in the root schematic, from this decoder. I added as much as information as possible during my reverse engineering, so to understand what's going on as much as possible. The clock generation part is quite involved too. There are 3 phases of 6.1 and so on megahertz clock. Sometimes a negated signal of one phase is used too. There is a 3.072 megahertz clock that is common to all the CPUs, and some other phases delayed or not of 1.5 and something megahertz, which is used to access the shared bus. So actually the shared bus can be accessed only on the high phase of this clock 1.5 or some delayed forms of it. It's not very clear, but it's clear enough that I can troubleshoot this part now that I have the schematic. And I believe the CPU has not issues. Well, that's my guess, because when it's service mode, the controls works fine. Every control works. There is no stuck input that I can find. So also dumped this ROM, disassembled the Z80 code from this ROM, and tried to comment as much as possible this code to understand what could be the difference from the machine in service mode or in the normal game mode. But this CPU is not very aware of the particular what's going on externally. I mean, it's just getting NMI signals when the other CPU are requesting data from the inputs, and it puts the requested data on the shared latches. So it's not very aware of the external world, that I could understand at least. So what I believe is, since there is some involved mechanism to allow every CPU to access the shared bus with some priority, so the CPU1, the master CPU, has the highest priority, CPU2 is the second, and this is, which is the CPU3, has the least priority. And what happens is, when this CPU wants to access the shared bus, it rises what I call the memory request tree signal. But if on the same clock phase there is already a memory request from the CPU1 or CPU2, this gate arrangement makes the wait signal for this CPU go low, which means the CPU will halt until the next clock phase, positive clock 1.5 megahertz phase. So it will wait until the bus is freed from the other CPU holding the bus during this particular clock phase, and then continue in its bus access after on the next clock 1.5 phase, basically. But the address bus enable generation, the clock phases generation is quite involved, and it's duplicated on each chip CPU. This one a job for the custom chips on the original Galaga. So I believe that during the service mode, most of the CPUs, excluding of course the first one, are not working. Mostly idle. But during the game, of course, all the CPUs are trying to access the shared bus. Probably some part of this priority method, clock delay method, and so on, it's not working probably correctly, and that means that there are some conflict on the shared data bus or the shared address bus, messing with the game control access. That's my wild guess so far, but at the moment I have enough of the schematic reverse engineered to understand and check what's going on really. with this game.